Welcome back to The Explainer. Today, we're embarking on what I like to call the builder's journey. Together, we're going to explore the incredibly fascinating world of aquaculture engineering. We're going to look at exactly how experts take a patch of bare, undeveloped soil and transform it into a mathematically sound, completely zero-waste aquaculture pond. It is a journey that blends the raw, unpredictable forces of nature with the absolute precision of geometric math. Okay, let's dive right in. Here's our blueprint for today. We'll start with site selection and surveying, move on to the anatomy of dikes, then we'll get into calculating deck geometry, followed by seepage control, and finally we'll wrap up with zero-waste earthwork math. Part 1. Site selection and survey methods. Before a single shovel even touches the earth, engineers have to get out there and survey the bare ground. They rely on baseline surveying methods right in the field to figure out what they're working with. First up is pacing. This is essentially measuring distance by counting your footsteps. It's a quick, rough estimation tool. For exact distance mapping, engineers step it up to taping, using specialized engineering tapes. And finally, there's differential leveling. This one is absolutely crucial for determining the elevation profile of the land. You have to know exactly how the ground naturally rises and falls if you want to successfully manage gravity and water flow later on. To actually pull those methods off, they need the right gear. Engineering tapes handle those precise distances, while an auto level or transit paired with leveling rods gives us those critical elevation metrics. But honestly, perhaps the most important tool in the entire kit is the soils testing kit. You literally cannot build a massive water-retaining structure without testing the dirt first to map out its geotechnical suitability and texture. If the dirt is wrong, your whole farm is just going to wash away. Moving on to part 2, anatomy of aquaculture dikes. Let's look at the actual physical barriers of the farm. What's really wild here is how perfectly this shows that not all walls are created equal. The hydraulic load and the external wave exposure dictate some massive size differences across the facility. Your main or perimeter dike is your frontline defense against tides and storms. Because of that, it needs a massive crest width of 3 to 5 meters just to hold the line and allow heavy machinery access. Secondary dikes are quite a bit smaller, usually 2 to 3 meters wide, because they're designed merely to segregate internal canals. And finally, tertiary dikes just outline small, low-stress nursery systems, requiring only 1 to 1.5 meters of crest width. Woven right into these dikes is a network of gravity-driven canals, and getting the gradients right on these is an incredibly delicate balancing act. Engineers typically aim for a 0.1% to 0.2% slope. Why? Well, if the slope is too steep, the water moves too fast, causing what engineers call tractive force erosion. That literally means the water washes the canal banks right away. But if the slope is too flat, the water stagnates. That leads to oxygen depletion and massive pooling of microalgae. It has to be just right. All right, part 3, calculating dike geometry. So we know what these structures do. Now we hit the drawing board to make sure they don't just collapse under their own weight. The first big mathematical hurdle is a structural phenomenon known as geotechnical settlement. When you dig up soil to build a dike, it gets fluffed up, it's full of air. Over time, gravity, moisture, and natural compaction cause that soil to consolidate. Think of it like a giant sponge being slowly squeezed. The dike's height will visibly shrink. Because of this, engineers are forced to calculate a compaction height allowance. They literally have to overbuild the dike so that when it eventually sinks, it settles right at the exact safe design height. Since we know we have to overbuild the height, it begs a pretty massive engineering question. How on earth do we calculate the exact base footprint required to support this enormous, settling trapezoid of dirt? Well, to solve that, we have to lock in the core variables of our cross-sectional geometric blueprint. First, we have WC, which is the crest or crown width at the very top. Then we have HC, the required construction height, which, remember, includes that extra soil for the settlement we just talked about. Then we have 2 absolutely crucial slope variables. SD represents the horizontal run of the dry, landward side, and SW represents the horizontal run of the wet, waterward side. Both sides must be structurally sound to handle totally different kinds of physical stress. And here is where it all comes together into one elegant formula. The base width, or WB, equals the crest width, plus the height multiplied by the sum of the dry and wet side slopes. It is genuinely impressive how neatly this ties everything together. The crucial takeaway here is that this math physically dictates the massive earthen footprint resting on the ground. If this base is calculated even a little too narrow, the entire dike will fail. Which brings us to part 4, controlling seepage with cores. Because, you see, a wide footprint alone just isn't enough. We have a hidden enemy here. Enter the phreatic line. This is the hidden top boundary line of seepage water naturally flowing horizontally through the earthen dike. It moves from the high-pressure wet side toward the low-pressure dry side. In a standard homogeneous clay dike, the saturation line slopes downward at a gradient of about 1:4 or 1:6. It's totally invisible from the surface, but it absolutely dictates the structural integrity of the entire farm. The danger becomes super clear when you compare an unprotected dike to a core-protected one. In an unprotected dike, if that phreatic line stays high and intersects the dry slope above the ground, in an area called the dry toe, it causes a catastrophic failure known as piping. Water literally carries the internal soil out with it, causing the whole wall to slump. The heroic engineering solution to this is the core-protected dike. This uses an impervious clay core trench to force that phreatic line safely downward, deep into the solid foundation. To actually build this protection, engineers dig a trench right down the center line of the dike. They cut completely through the porous, leaky topsoil until they hit the hard, impermeable clay subsoil below. Then they backfill this trench with highly plastic puddled clay. This creates a watertight seal that ensures the dry toe of the dike remains completely dry, totally stable, and secure against internal erosion. Finally, Part 5, Zero Waste Earthwork Math. Now that our dikes are rock solid, let's talk about how engineers save a ton of money and protect the environment using cut and fill mechanics. Think about how a single scoop of dirt physically changes volume during excavation. First, you have in situ soil. It's just resting undisturbed in the basin. Once excavated, it becomes loose soil, bulking up by about 20% because it's suddenly full of air. Finally, when heavy machinery presses it into the dike, it becomes compacted fill, shrinking back down tightly. Engineers must track this shifting volume perfectly. By tracking those volumes, they achieve a zero-waste mass balance. The rule is simple in theory, but incredibly tough to execute. The compacted volume of soil excavated from the pond basin must exactly equal the compacted fill volume required to build the dike walls. If you perfectly match the cut with the fill, you completely eliminate the astronomical cost and environmental damage of hauling thousands of tons of dirt onto or off of the farm site. So, this sets up the ultimate puzzle for the aquaculture engineer. Taking all this structural geometry, settlement factors, and soil shrinkage into account, how deep exactly do we need to dig into the ground to hit that perfect zero-waste equilibrium? The answer is right here in the zero-waste cut depth equation. The design depth of the cut equals the total required dike fill volume divided by the area of the pond multiplied by 1 minus the compaction shrinkage factor. This equation brilliantly takes every physical transformation, the area, the required volume, and the mechanical shrinkage of the earth, and distills the whole shebang down to a single actionable number for the excavator operator. In one of the real-world optimization case studies from our sources, after punching in all the specific pond dimensions and soil metrics, the math spits out exactly 1.48 meters. It's that thrilling aha moment in engineering where abstract math becomes a physical reality. If the excavator bucket digs exactly 1.48 meters down across the basin floor, the farm will have the exact amount of dirt needed to build the dikes. No waste, no shortages. Which really brings us to this beautiful summary from the course materials. By mirroring the real-world sequence of building a closed-system farm, abstract formulas anchor into a physical, easy-to-visualize reality. We've literally seen how massive physical forces, from crazy water pressure to soil bulking and geotechnical settlement, get elegantly tamed and solved by these geometric equations. But I want to leave you with a bit of a provocative thought to chew on. We've just explored this perfectly balanced mathematical blueprint. But if our zero-waste formulas depend on perfect, predictable soil compaction, what happens when extreme, totally unpredictable weather, like a sudden monsoon or a historic drought, radically alters our soil settlement factors mid-construction? It really highlights the endless, fascinating battle between precise engineering and the sheer unpredictability of nature. Thanks for joining me on this explainer, and keep exploring.